future, we've talked about the challenges affecting the industry. One of the major challenges affecting the industry is the CO2 emissions impact from cement manufacture, which is huge. However, behind the scenes, Britpave members, CEMEX, and we'll also hear from Tarmac, are doing considerable work to reduce that CO2 figure. And I'd like to now invite Steve Crompton from CEMEX, who's going to outline some of the developments and innovations that they're doing there that can help reduce the CO2 of cement manufacture. Steve.
Thank you very much, Steve, and it's a real pleasure to be here in person and not presenting on Teams for the first time in what seems like forever. Pretty well all the previous speakers have talked about the impact of carbon from cement and or concrete, and you know, if you're a cement manufacturer in today's world, the number one item on your agenda is global warming. And I think if we were to roll back 10 years, there was a lot of skepticism around global warming. Was it really man-made? But I think there's now a general acceptance that global warming is a key issue for the whole of society. And what I want to share with you over the next 20 minutes is just what the scale of that challenge is for cement and concrete, and what the industry is doing about it and what the industry is committing to. What we've seen is that, you know, with the growing acceptance of climate change, that governments around the world are beginning to implement policies that are requiring industry in particular to reduce its CO2 impact. And you'll see on the slide there, well, I'll not go through the details, this is taken from a government publication, and you know, on how they're intending to reduce CO2 in the UK to effectively net zero by 2050. And although there's a lot of focus around transport and power in the government policies, there is an expectation that all industries will contribute to this. And, you know, all of industry will be required to do this. It's, you know, if you look at particularly on cement and concrete, there is a fairly negative perception around it. But again, even whole construction, we're beginning to see the impact of CO2 policies. And we see, for example, you know, the Heathrow expansion a couple of years ago was overruled ruled illegal because it didn't take into account properly what was happening around climate change. And if you look at, you don't have to look very far to see some fairly negative headlines around concrete. You know, that first one there, some of you may have seen all the stuff. This was a big article or series of articles in The Guardian that talked about concrete being the most destructive material on Earth. You know, a claim here that it accounts for 7% of global emissions, larger than aviation, for example. And, you know, more pollution coming from cement than all the trucks in the world. Now, you know, some of it's exaggerated, but there is an underlying truth in the matter that the cement industry does produce round about between 5 and 8%, depending on whose figures you believe, of global CO2 emissions. So it is a significant contributor to CO2. And the industry recognises that. And although, you know, this again taken from government numbers would suggest that, you know, concrete and cement is relatively low in the UK terms, I think globally it is accepted that the number between 5 and 8% is a fairly accurate number of what is coming from existing cement production. So what is industry doing about this? You know, we've been working on this for a number of years now, and this is a UK, but I could have picked out any country in Europe or even the United States. All of these industries in those countries are developing and publishing plans for their commitments. And in the UK, you know, it's really around 7 main areas, looking at, you know, the emissions from power into the cement works in particular, looking at how we can decarbonise transport networks, low carbon cements and concretes, which I'll focus on a little bit later in the presentation, fuel for the manufacture of cement, a big issue around carbon capture, and in the longer term, and something that, you know, although I'm not really going to cover too heavily today, is around carbonation. I think, David, you mentioned the titanium dioxide absorbing particular nitrous oxides, but let's not forget that exposed concrete will naturally absorb CO2 by the process of carbonation, and particularly relevant, obviously, when you're looking at roads which are exposed. And also the benefits of concrete as in terms of thermal mass for the ongoing reducing operating and energy costs of buildings. And if you look, how do they, each of those contribute? What is the scale of what can be achieved by these various initiatives? If you're looking at the indirect fuel usage and energy usage, the target is to reduce that, overall reduce CO2 by 4% by the initiatives in that area. CO2 for transport is a further 7%. Low carbon cements and concretes actually will reduce a little bit more than that, and they'll do around about 12%. Fuel for manufacture of cement, a further 16%. But the big ticket item really is around carbon capture. And that is where the true benefits are going to come in the next 30 years. If you look at this, and it's a bit of a detailed diagram in a way, but what I wanted to really share on this one is on the left-hand side is all about cement manufacture and what you can do in cement manufacture, some of the initiatives, and we'll talk a little bit about them in a minute. And on the right-hand side, what you can do as standalone within concrete. But the two are obviously inextricably linked. And in terms of the division between these two, 80% of the carbon is coming from cement manufacture. That's where most of the carbon is coming from. And then there's a further 20% coming from concrete, really determined by the types of cements that are being used, the amount of recycling, energy use in the production of ready-mix concrete, for example. And in order to get to the 2050 target, these both sides of the industry are going to need to work together. And I think it was mentioned in earlier presentations, not only do we have to work together with cement concrete, but we also have to work with the wider industry, with contractors, with clients, with specifiers, to really adopt some of the changes that are outlined that are coming. So we focus on the kind of short-term targets. When the government targets in the UK for net zero by 2050 are actually broken down into sort of 5-year target cycles, and they would claim that the current 5-year we're on target. By 2030, we're not currently on target to meet that particular target. So the cement manufacturer really has also broken down their targets in the short to medium term. And if you look at cement manufacture, what they've been doing, alternative fuels is a big one. Historically, cement kilns fueled by coal, petcoke, traditional fossil fuels. And over the years, that has been changing, and that's been in for a number of years now. So fuel being replaced by municipal waste, by animal waste, I think you mentioned earlier, David, industrial waste. The cement plant down the road here at Rugby, almost 80% of its fuel actually comes from recycled household waste. So there's a plant actually built next door to the plant to take household waste, recycle that and feed it directly into the kiln. There are other plants that are over 80% recycled fuel usage, and increasingly looking at hydrogen as a source of fuel, which can be very beneficial indeed. And the Ribble example that was highlighted earlier in the day, they've achieved net zero through their kiln by a combination of using recycled bone meal and other recycled fuels along with hydrogen, and that is the key driver to get it towards the net CO2. Other things you'll be familiar with, clinker factor is a cement term that's used, effectively how much CEM 1 type material is in there, and increasingly we're seeing, over the years, more fly ash, more slag being used, and increasingly limestone. But they bring with them their own challenges. Fly ash derived from coal power fire stations. Well, there aren't very many of them operating in the UK anymore, and across the world we're seeing that coal-fired power stations are being substituted by alternative types of power generation. Slag, again, a nice way of reducing carbon, but slag also is becoming more of a difficult material to obtain, partly because the steel manufacturers themselves are looking at ways of reducing CO2, and one of the ways they do that is to move to electric arc furnaces, and therefore there's no slag being produced. So increasingly what we see is that the materials that we've relied on to give us lower CO2 actually becoming more difficult to obtain. So certainly in the longer term, we'll have to look at alternative materials. In the short term, they're still here, and what we are seeing is increasing use of combination cements, multiple blending of cements, so, using fly ash and slag together, perhaps in combination with limestone, and a general phasing out of CEM 1, which is the highest CO2 cement that's produced at the moment. And also other sort of secondary effects, really, with things like thermal efficiency on producing lower temperature clinkers to reduce the amount of CO2 that is produced. And if we go on to, because that only gets us so far, probably gets us about halfway to where we need to be by doing all those things on the previous slide. If we want to meet the 2050 targets, then we've got to think a little bit bigger. And, the big areas all around carbon capture. And if you look at a bit of detail on carbon capture, it's worth looking. If you look at the diagram on the right there, at the bottom, that one, the box number 1 there, in terms of how the amount of CO2 that's produced in cement manufacture, around 40% of it is associated with the heating up of the kiln, the raw materials that are used, but 60% is actually the chemical process, transforming the raw materials into cement. The chemical reaction releases CO2, and about 60% of that is 60% of the CO2 is generated by that reaction. So what the industry is now looking at is how do we capture that CO2? Carbon capture is a relatively new technology, particularly in cement manufacture, and there are a number of different technologies that are currently being looked at around the world. There are several pilot projects across Europe looking at these. There's 4 listed there. People looking at different methods, which are the most applicable to our industry. But there are some big challenges with this. This is not cheap technology. This is very expensive technology, and to scale it up to cement works is not going to be cheap. And also, it's a relatively early stage technologies for use in our industry. And even if we get it to work, and the industry is confident it will work, we then have to have an infrastructure to, having captured that carbon, what do we do with it? And I think one of the earlier speakers talked about, producing fuel from it, and that's certainly one of the options. Also being used in the chemical industry, can actually be used to manufacture artificial aggregate, effectively make an artificial limestone, which can be reused into concrete, which is a nice kind of circular economy approach to it. So, there's a lot of work to be done, but the prize from carbon capture is huge. And, there is, I think, a growing realisation that if we want to carry on using these materials, and then the industry may well need a commitment from governments to help to fund some of this very high cost of carbon capture. If we go on to concrete, what do we do? For many years, and I'm sure many of us in this room have utilised blended cements, greater usages of slag, fly ash, very high blend levels. But as I said before, those materials are becoming increasingly difficult, and in the longer term, there are question marks of how much of that material will be available. So we need to look at alternatives to that, and there's a lot of work going on at the moment looking at activated clays, for example, natural pozzolanic materials, and recovered fly ash. There are many power stations around the UK where there are lagoons of fly ash, and work has been done in the past by a number of companies to recover that fly ash to reuse it in concrete. Historically, the issue has been really around the cost of that, and it not being cost effective. However, as we see the cost of these secondary cementitious materials increasing, then maybe their time has come and there will be an economic incentive to reuse these materials. Geopolymer concretes or alkali activated materials are also another area, and I noticed in a couple of the earlier presentations they were referred to. Geopolymer concretes, what is it? Well, they're effectively concretes manufactured without any cement clinker in them. Typically, they're manufactured with slag or fly ash, metakaolin, which is a kind of activated clay, or combinations of those materials, and they're activated chemically, usually with sodium or potassium silicates or hydroxides. They can be used in conjunction with conventional admixtures to control the properties of the material. Often they contain limestone fillers as well, and obviously water to get the whole reaction going. What are the benefits of these materials? Well, they are lower CO2. There's no cement clinker in them at all. But don't be misled into thinking that these are zero carbon concretes, because they're not. There is carbon in slag, for example, and the activators themselves are very, very high in CO2. In fact, they're probably a scale 5 to 6 times higher than you get in cement, but you're using a much smaller amount of it to activate the material. But nonetheless, you can get down to possibly below 70 kilograms of CO2 a metre, compared to round about 200. Mike used a figure of 208, which I would agree with. Typically for a blended cement concrete, you'd be round about the 200 mark. So, they do offer a significant reduction on what might be considered a conventional concrete. There are some drawbacks. Health and safety wise, the chemicals are very difficult to handle, and you've got to be very careful with those. As I said, the activator is very high in CO2, and some of the formulations are susceptible to low temperatures. Bearing in mind, particularly if you've got effectively 100% slag as your material, then that can be sensitive to lower temperatures. Current cost, they're more expensive than conventional concretes. But as we get economies of scale and more usage of these products, one would anticipate the cost would come down. And perhaps the biggest barrier actually is they're not covered by any national standards, and that makes it difficult for people to use them. And often when we talk to potential customers who are quite excited by these products, when they realise there's no standards to cover them, what the implications of that is for their public or product liability insurance, they tend to shy away from these products. And what we find is they tend to get used as demonstration projects, get used in non-permanent works. I think in one of the highways presentations earlier, talked about using it in drainage channels. And that's the type of things we're seeing this being used at the moment. And perhaps we need to have a bit of a sea change to think that we adopt some of these more innovative materials. And just to I'll very quickly go through these, and just to show you that these products actually can perform very similar to standard concretes. Setting time, they do set quicker, which actually can be an advantage, but you can control it with admixtures. Consistence retention, this is comparing it to a more standard concrete. And again, these can be controlled with the right admixtures. If you didn't have any admixtures in, they have a tendency to lose consistence very quickly. Strength-wise, this is a straightforward comparison. 50, 60 megapascals quite easily to achieve. There are some formulations on the market that would claim to go up to 80, 90 megapascals. So for most applications, these types of concretes can deliver the strength that most people are looking for. Flexural strength, much the same as you would get with standard concretes, perhaps no surprise there. And water penetration, resistance to any penetration of chemicals is good, slightly lower than standard concrete in the test work done on this particular sample. Drying shrinkage is much lower, and again, that's because it's a completely different chemical reaction to cement reaction, and so drying shrinkage is almost negligible. And they're slightly stiffer than normal concretes, given a higher modulus of elasticity. And the one area that is often asked is around, well, these are alkali activated materials. Are they resistant to ASR? And on the testing that we've done, we've seen that they are slightly higher expansion than you would get with a traditional blended cement. So, this is compared against a fly ash based cement. And it's slightly higher, but lower than the limit. The limit is 0.1 for deleterious ASR, and so it's below the limit. So something to be aware of, but generally, and certainly a lot of the literature would indicate that they're not susceptible to alkali silica reaction in the way you may expect. Looking at it, just as a quick summary, the little video playing there is a geopolymer concrete. And to be honest, if you didn't tell the people on site that it was anything different, they wouldn't know. It looks, flows, places like normal concrete. Be a little bit careful in cold weather with it. And, the hardened properties are very similar to standard concrete. And just to reinforce that, we're seeing the adoption of this technology being constrained by the lack of standards, which actually has been addressed. There's work going on at a European level to develop standards for this. The cost at the moment can be off-putting, and sadly a lack of long-term data in service, something that often we come up against. And I have to say probably more in the UK than I see elsewhere in Europe, that with new novel products, people are a little bit reticent to use them. And I think as an industry, we've got to try and change that mentality if we want to address some of the issues. In terms of concrete technologies, I think there's more to be done with admixture technology on how that can focus on reducing CO2, and there's certainly a lot of work going on in that area. And as I briefly mentioned, carbonation, I think, is a long-term. If you're looking at the whole life, then one should also consider the impact of carbonation. Recently you may have seen that the IPCC put out a press release that concrete actually absorbs 50% of the CO2 that's produced in its manufacture. I think that's a claim that some people would dispute such a high number, but nonetheless, I think the principle of concrete absorbing CO2, when you look at the whole life costing, much in the same way as Mike showed us earlier, then carbonation should not be ignored. Some of the more sort of playing around the edges, because if you look at what I've talked about so far, probably is going to produce the 70-80% reduction that we need. But there's other things to be done around circular economy, more use of recycled materials, use of crushed concrete. And although we see pockets of that, it's still not huge in the industry, particularly in this country. And other things around the fuel supply chain, on using renewable energy and using restoration to when we extract materials. I'll just summarise really what we've talked about, kind of rush through a little bit on some of the initiatives that are going on. But there is no doubt that what we see, not only in government policy but society at large, has really highlighted the issues around the impact of our products, and the industry has responded to that. We've already made a lot of progress. And I was glad to see when David presented a number of 53% from 1990, that it's exactly the same number that I had in my presentation. So yeah, there's been a lot done since 1990. Some of it, let's be honest with ourselves, back then wasn't being driven by CO2 reduction. It was being driven by efficiency. It was being driven by cost savings. But nonetheless, when we look back at what we used to do in terms of carbon when it wasn't such a headline issue, we have made great progress. And certainly in the last 4 or 5 years, it has become the headline issue across the industry. And the industry, certainly in this country and across most of the Western world now, is committed to producing net zero concrete by 2050. In concrete side of it, it's around development of blended cements, use of alternative secondary cementitious materials, further developments in admixture technology, and hopefully we'll see more of the geopolymer technology coming along. I think that has impacts for the way we use concrete. It's some challenges we saw in the highways repair section, having 25 megapascals at 4 hours. That kind of feels difficult if you've got very high levels of cementitious materials and non-cementitious materials in there. But these are the challenges we've got to face. Cement, I think, is really where the big wins are going to come. More alternative fuels, hydrogen technology seems to offer us a lot of opportunity to reduce CO2, and I think we'll see a greater acceleration towards blended and multi-blended cements. We'll start to see the likes of CEM 4, CEM 5, even CEM 6 type cements on the market. Increased use, particularly I think, of limestone cements. hopefully starting to replace someone. And other action, perhaps the big takeaway is that the real progress is going to come when we see carbon capture start to be operated at cement works around the world.